Good morning. Our first talk is from Gautam Aishwarya. He will talk to us about the Shannon-Kneser-Poulsen theorem.
Thank you, James. And, thank you for coming to my talk. And please stop me whenever you have questions, of course. So this is joint work with Dongbin Li, who is at University of Alberta. And so here is a question. So I have some balls in space of fixed radius, and xi's are the centers of those balls. Now if I bring the xi's closer to each other, if they become yi's and now they are pairwise closer to each other, then what should happen to the volume of the union? So it seems from the picture and intuition that the volume of the union should decrease. And so this is open. This is called the Kneser-Poulsen conjecture. So the thing that I really showed you is true because it's known in the plane. My picture was on the plane, but in general in n-dimensional space, n bigger than or equal to 3, this is completely open. So we don't know about this. Now, let me tell you about an information transmission problem. Suppose I have these stars, and if I want to communicate with you, I can light one of these stars. And however many times I want, and we will decide beforehand what lighting this 5 times and then lighting this 1 time means and so on. I can light these stars. So this is the communication model. Okay, I can light this one, I can light this one. But when I light a star, what you receive is not exactly the star that I lit, but you receive something which is Gaussian distributed with that center. So you can think of this as, you release a particle and you detect it only after time 1, and in the meantime the particle is doing Brownian motion. So I'm trying to convince you that it could really be a real life problem. So you do this, but what you see is probably this point, in which case you can tell, yes, sure, this was coming from there because you know that the noise is Gaussian, but you can get this, which you won't know, and so on. So the question that I want to ask is, if I bring these stars closer, should communication suffer? So does communication over an additive white Gaussian noise channel worsen if you bring the transmitters closer? And this is a question that I will answer today, that this is true. Okay, so now I will, any questions about the advertisement so far? So now I'll tell you more about the Kneser-Poulsen conjecture. So this is more precise version of what I just showed you on the first slide, that if I have points x1 till xk and y1 till yk, and all the pairwise distances are smaller, then the volume of the union will decrease. And so I will just say decrease. I will say I will not say non-increase. So this will be my usage of inequalities. Okay, so this is the Kneser-Poulsen conjecture. So this is what we'll talk about. So there's another very interesting related conjecture about the volume of the intersection. This is called Gromov-Klee-Wagon conjecture sometimes. And this is something I won't talk about today. Unless you ask me questions, in which I will not resist the temptation to talk about. Okay, so these are two conjectures. Now, some history about all of this. So this started with Kneser and Poulsen in the 50s. So this is the original conjecture, and this conjecture is always, these days it's treated with different radii. But for me, all the radii will be the same, as in the original formulation of the conjecture by Kneser and Poulsen. So you can talk about this with different radii on each pulse. So, some developments, and I'll skip a lot of them. I'll just tell you a few very important ones. important ones for this talk, say. So Chicos proved this conjecture under the assumption that like there's a initial setup of points, there is a final setup of points. He proved it under the assumption that you can continuously move these points from the initial configuration to the final configuration such that all pairwise distances reduce under this motion. So this was Chicos in 1998. So he proved this conjecture in this situation. But all contractions are not realizable this way. For example, if you do a reflection, then I don't see how you could continuously move some set of points in the, say, upper half plane to the lower half plane with a continuous motion. So there are counter examples. So this is Chicos for continuous contractions. Soon afterwards, it was proved in the plane by Bezdek and Connelly. So Bezdek and Connelly used formulas of Chicos, and they used one trick which will be useful to us as well later, to realize contractions in Rn as continuous contractions sitting inside R2n. So this is the second ingredient of Bezdek and Connelly's proof. And the third one is what Tomasz told in his talk, the Archimedes principle, that if you have a d plus one dimensional sphere, and if you project onto, d plus two dimensional sphere, and if you project onto the d dimensions, then the projection is really the uniform distribution on the ball. So something like this. This was the third ingredient, of course, very artfully combined to prove it in the plane. Because in the plane, d plus 2 is equal to 2d. So this is Bezdek and Connelly. And then it was proved under various assumptions on the contractions, which I will not get into. I will not describe what these things exactly are. But on very special conditions on the contractions, the Kneser-Poulsen conjecture is known. But we are very, very far from resolving the Kneser-Poulsen conjecture, even in R3. Okay, so this was some history. And now I will, so you can look at this survey paper called 4 Classic Problems, or this one was uploaded on arXiv like 3 days ago. So these are 2 very good survey papers so this has a lot of information, but if you want a very quick review of what is known, you should maybe look at this one. So in 1.5 pages or something. Okay. So now I will rephrase the Kneser-Poulsen conjecture in a language that I like. So recall that my points xi's were going to yi's. So what I'm saying is that if I call this T, then the map T is one Lipschitz. This is what I'm saying. And now we know that we can describe the Minkowski sum of 2 sets, which is just pairwise sums. So in this language, the union of the balls in the first configuration is exactly the set K, which was a set of all the xi's, plus R times the unit ball. This is original thing is K plus RB. And the final configuration is T of K plus RB. Okay. And also, I need not just talk about the contraction being, so I will call one Lipschitz maps contractions, even though the Lipschitz constant name is equal to 1. So terminology. So I need not only talk about T being defined on K, because Kirsch-Braun tells me I can define it on all of the space. Cage-Braun extension theorem tells me that I can extend a Lipschitz map without losing anything on the Lipschitz constant to all of the space. So this is the Kneser-Poulsen conjecture, that in a language that I like, that if you have a contraction T of Rn and you have a compact set, then the volume of the tube around K should be bigger than the volume of the tube around Tk. So this is one of those questions where, of course, if you have a contraction K to Tk, it's trivial that volume reduces, surface area reduces, and whatnot. But now the question is, if you perturb both objects by something natural, can you at least ask for some very coarse invariants such as volumes to still be comparable? This is one viewpoint. So now it is also not known for convex bodies. And this is not, it seems to me that this is not something that was cared about very much, but because the original conjecture is about discrete set of points. But even for convex bodies, I don't know if this is true. Any question? Yes.
So is this equivalent to the other conjecture?
Yes, with all radii same. So in my talk, all radii will be the same. Because of course, if K is finite, it's all good.
Okay.
If K is compact, I'll approximate it from the inside by more and more points. So this is the same thing. And now I will say some words about the relationship or the parallels between convex geometry and information theory, which will help us formulate an entropic version of the Kneser-Poulsen conjecture. So these parallels were observed by Lieb and Costa and Cover. So they observed parallels between Brun-Minkowski inequality and the entropy power inequality. And in my talk, it will be more like the geometry of sets imitates the geometry of information. So this is one direction which my talk is about. Sometimes you can think of probability as extending geometry. For example, if you think about optimal transport, so this is a viewpoint where probability theory extends geometry. You can think of volume as maximum entropy, and then displacement concavity of entropy implies Brun-Minkowski and so on. But this is not what my talk is about. It's about the second bullet point. And of course, I should sooner or later define the entropy, which is integral minus f log f. Now, what is the Brun-Minkowski inequality? It says that the volume of the sum set over 1 to the power of 1 over n is bigger than the same quantity for individual things. And one way to look at it is it tells you that the sum set spills out least if things that you're summing have some structure. So if A and B are balls with the same volume as A star and B star are balls with the same volume as A and B, then the volume of A plus B is bigger than the volume of A star plus B star. This is the Brun-Minkowski inequality. And the entropy power inequality, on the other hand, is this thing over there. So this is just like volume to the 1 over n, 1 over dimension, is volume radius. It is the radius of the ball having the same volume as the set. So similarly, entropy power is the variance of the Gaussian having the same entropy as x. So we can restate this entropy power inequality in this language as in Tom's talk, that if x and y are independent random vectors and x star and y star are Gaussians, so if they have the best possible structure, then their sum set spills out the least, where the notion is entropy.
They have to have proportional covariances in this case.
Yes, yes, with proportional covariances. So now, so this is the picture, right? So in geometry, I have sets. In information theory, I have random vector sets. In geometry, I have Minkowski's sum. This is paralleled by independent sums of random vectors. There is volume. There is log entropy, which I just wrote down as entropy. And the Euclidean ball becomes the standard Gaussian in this analogy. And so the volume of the tube is parallel to the volume along the heat flow, x plus square root sz. This is the, so this was the Kneser-Poulsen conjecture. And what I'll prove for you is that if there is a contraction on Rn and x is any random vector, then, so if s was 0, it is again trivial to see that the entropy of the one Lipschitz image is smaller. Not only entropy, but everything, right? But what I will prove is that even if you now flow both of them along the heat flow, these entropy comparisons persist. And I will not write Renyi entropy, but everything that I'll say will also hold for Renyi entropy. So this is also for Renyi entropy of arbitrary order. So any questions so far? So now I will start proving this theorem.
Will it be true for other entropies?
So by other entropies you mean like Renyi entropy? It is true. It is true. So if I replace this by H alpha, it will be true. So we'll see soon why actually. Okay. So now step 1 is to prove it for continuous contractions. So let me remind you the definition of a continuous contraction. A continuous contraction is a homotopy. So T is a contraction. I will call T a continuous contraction if you can build a homotopy from the identity to T such that all pairwise distances reduce along this homotopy. So in this case, so is this clear? Because this is the most important thing. Okay. So now if I stop at time t, if I take a snapshot at time t, I have a one parameter family of maps which are continuously contracting. This is what I'll call a continuously contracting family of maps. And they are everywhere. So for the real Kneser-Poulsen people, it's a big restriction because discrete set of points you rearrange. Not every contraction is a continuous contraction. Very true. But in probability theory, almost every contraction is a continuous contraction that I know of. I mean, of course, there would be examples. It's such a vague statement. For example, if you look at, if you know that the Brenier map is a contraction, then it is a continuous contraction. You can see that it's a continuous contraction. And for example, in this Kim-Millman construction of strongly log concave to Gaussian, if you do the Ornstein-Uhlenbeck flow. So the Kim-Millman argument basically is that it is a continuous expansion. So I'm yet to find a natural example in probability theory of a contraction which is not continuous. Yeah, many examples. And what do we want now? If we want to prove it for continuous contractions, we want to show that this quantity is decreasing in t. This is what I want to show. This is step 1. So what do? So the tool that I'll use is flow of measures, and I will I will take a curve mu t in the space of probability measures, and so I will be very careless with regularity here, because in the end, the thing for which I have to use all of this can be made as regular as you want, pretty much. So please bear with me that if mu t is a curve, I will call Vt some time dependent velocity field to be compatible with mu t if it satisfies this conservation of mass equation. So this is saying that the amount of mass changing should equal the flux. So this is what I will call compatible. And like sometimes you write this should be understood in the weak sense. So this is a definition. This is a definition of a compatible pair mu t comma Vt. Any questions? So now an example. So if I fix a measure mu naught, and if I have a one parameter family of diffeomorphisms t sub t, then I can look at mu t's which are just flowing along this one parameter family of diffeomorphisms. Then what I can do is, so I just wrote if x is a random vector for people who would like to think in terms of random vectors, x is distributed according to mu naught, then mu t has the distribution t sub tx. So then I can define a velocity field which by solving this equation. So I can define a velocity field by solving this equation, and this velocity field will be compatible with mu t. So are we all good so far? Or would someone like me to make some more comments about this? Okay, so this is just calculus things. So now, so this is one natural way of looking at these flow of measures and numbers. So now I need to know something, because my starting velocity field, remember that I'm trying to talk about continuous contractions. So I need to know something about their velocity fields to do anything with them. And very easily you can observe that they have a certain monotonicity property. That if Vt is a velocity field corresponding to a continuous contraction, then Vt is monotone in this way. So this you can check by differentiating the distance squared. Now, so one small remark that I want to make, which may or may not be useful to people and will certainly not be very useful to me in the talk later, is that continuous contractions locally in time look like optimal transport contractions. So continuous contractions will do whatever they have to do, but and optimal transport maps travel along straight lines. But if you infinitesimally stand at a point and look at what's happening, so this is like an optimal transport contraction. So I feel, and we didn't have to use this, but I feel that if you ever want to prove something about continuous contractions in general, one may want to probably prove it for optimal transport. When I say optimal transport, I mean quadratic cost. So one may want to prove it for optimal transport contractions first, and at every time just approximate it by do a linear approximation. I think this can be useful in certain cases. Okay. So now I know what velocity fields of continuous contractions look like. But what do I have? I have t sub tx. I know what the velocity field of t sub tx looks like. I need to know what does the velocity field of t sub tx plus z looks like. So I need to know how are velocity fields perturbed under convolutions. So for this, one can compute this, and so in one language one can say, so my Vt was the original velocity field, and mu t was the original curve of measures. And this is in general, like it does not require mu t to be a contracting family or whatever, just in general. And if now my mu t tilde is mu t convolved with nu, some measure. So I had a curve, I convolved everything with some measure nu. Then I can write down explicitly what Vt tilde is, which is a velocity field compatible with mu t tilde. And in analysis language, this is exactly this. If nu has density g, this is what we are looking at. So this is exactly what we are looking at. So now I know what I knew something about the original velocity field. I know how it is perturbed under convolving with something. And so the last thing I want is what to prove in order to compare entropies. So then the third piece is that if you have a curve of measures which flows via this time-dependent velocity field Vt, then, and if I denote the density of mu t with respect to the volume measure by rho t, then if f is any convex function, f be any convex function which is 0 at 0, then negative divergence of Vt implies that these convex functions of densities are increasing. This is the third piece. And so if you wanted to get monotonicity of entropy, you would apply it to x log x, which is a convex function. If you wanted to get Renyi entropies, you would apply it to this piece. And so this is what we would like to prove in any circumstance when we want to show that entropy is monotone along a flow. Alright, so now I'll put everything together. And so I have a continuously contracting family of measures given by Vt. And now I also have a velocity field for the convolution by a formula. So the natural thing is to compute the divergence. And this can be done. And the divergence turns out that you can nicely write it in terms of a certain other random vector. So this is what the divergence is. So now, do we see something here? This is very much like the monotonicity requirement. And let me point out here that so this is for Gaussian, right? So I did convolution with Gaussian. So I just want to point out that if I did not have Gaussian, so this formula is for Gaussian convolution. If instead nu had density e to the minus v with respect to the volume measure, then my formula would look like this. So what do I? this. So the point is that for that formula, and in a minute let me check if I wrote this correctly.
The sign is wrong.
Yes, the sign is wrong. Sorry, I should not skip any steps here. I'll just write the right thing and let's see. So the right thing to do is to look at the formula for the velocity field. So I just needed to take a covariant gradient and then take the inner products and move the gradient to this thing. So what I would have is this is what I would have. Okay, so what I've written here is just taken the covariant gradient and then taken the trace. So as you can see, if V is the Gaussian, so I know grad V is just X. So a lot of rearrangements can be done to get the result there. So the reason I'm also mentioning this to you is because we were not able to do it for, I believe it may be doable for radially symmetric log concave noises, but we couldn't do it in dimension bigger than or equal to 2. So everything that I've done works for any, so the final conclusion not just works for the Gaussian, but for any log concave noise in dimension 1. Okay, so I will continue further. I just wanted to point out that this really uses Gaussianness, that formula over there. So now it's exactly in the form that we like, but there is a problem there that quantity over there, the expected value of Vty, if it was Vt of expected value of y, we would be very happy, right? Because this is exactly the monotonicity property of the velocity field. So the observation here is that y minus Ey is a mean zero random vector, and this is a constant. So I could replace it by whatever constant I want to. So now I want to replace it by Vt of expected value of y. But Vt may not be defined at that point. Vt may not be defined at that point. So what we do is we use a theorem of Minty. Minty's theorem says that if you have a monotone vector function, the maximal domain on which you can extend it is a convex set. And since this was, it was defined on y and I wanted it to define an expected value of y, Minty works in this case. And I can write it like this, and this finishes the proof if T is a continuous contraction. So any questions? Okay, so I will now do step 2, which is for So I want to use higher dimensions. The point is that if I have, and this was also useful for Bezdek and Connelly, and this is a trick that goes back even further in the 80s to Alexander, that at least to Alexander, that if you have a contraction and there's a type over there, if T is a contraction Rn to Rn, so T is a contraction, not a continuous contraction. Then if I define these STs, these are a continuous contraction defined on a subset of R2n. So I had a contraction defined on Rn. Now I think of it as a continuous contraction defined on R2n, taking this Rn to this Rn. It's like so I use 2n dimensions to make an arbitrary contraction a continuous contraction. So now I use properties of entropy, that I know my result for a continuous contraction. So I know that entropy of x comma 0 plus z is bigger than S1 of x comma 0 plus z, because S is a continuous contraction. I write it out. So this is what it looks like. Now note that everything over here is independent, right? So this is independent of this is independent of this, and Z1 and Z2. So R2n dimensional Gaussian is just Z1 comma Z2, where Z1 and Z2 are n dimensional Gaussians. And so I can just, by tensorization of entropy of a product joint distribution distributes as a sum, I can do this. But entropy of Z2 and Z1 are the same, they are the same Gaussian. So I cancel them and then I get the result. So this is what we get. And here this tensorization actually holds for any Renyi entropy. So you get this result for any Renyi entropy. So now I want to just raise one point here, that if you remember one of the results that I used to conclude monotonicity of entropy, it works for any convex function. For a continuous contraction, I can show that there is a convex majorization type thing happening, but I cannot use this trick. So this result, at least from our proof, is only for Renyi entropies. You cannot use any convex function f to define an entropy and claim this from our result for an arbitrary contraction T. For a continuous contraction, sure.
Because of
the tensorization. Because x to the x1 to the alpha, x2 to the alpha is x1, x2 to the alpha. So,
But if you wanted to prove this for a different, something that wasn't Gaussian, if you could prove it for continuous contractions, you would have it for general contractions?
no.
No.
No. So Gaussian is very much used here.
Okay.
So this is why, yes. So Gaussian is very much used here, and maybe I'll make some comments later about this. So now I will prove for you, I will connect this to the original problem, the information transmission problem. So even though, you know, many people in the audience probably already know this in and out, but I will just say what channel capacity is. So this is the theorem, and noisy channels in information theory are modeled by probability kernels. So X is the input alphabet, Y is the output alphabet. This tells you that if little x was sent, then the receiver receives an output which is sampled by the image under this probability kernel. This is what a noisy channel is. And so in our case, what we are looking at is an additive Gaussian noise channel. So if I have some set of points, which is my input alphabet, and so my channel, every x maps to the standard Gaussian with that center. This is what's happening in this case. And so this is what a noisy channel is. And the capacity of a noisy channel can be defined in a very intuitive way by asking first for a encoding decoding scheme. So what I'm about to say until almost this point, if you would believe a formula that I will tell later, you will not need it, but just for completion, I will tell you what this thing is. So an epsilon code of length m is a disjointification of the output alphabet and some choices of the input alphabet. So how you should interpret this is, if you receive something in DI, you tell that you infer that XI was sent and you should do it in a manner which is reliable.
Xi is in DI or?
No, XI is in X, fancy X over there. So you're receiving something in Y and you want to tell what was sent. So this is your decoding scheme. So NW epsilon is the length of the longest epsilon code possible. So this is essentially how many of the XIs can you reliably transmit when you use the channel once. So now what you can do is you can make products of the channels, because no one told you that your language should only be in terms of the x1, x2. You can look at the product space and that may at times improve communication. So if I wanted to communicate to you 5 and with binary it became 6 or 4 with probability say 0.2, then if I communicated 500 times to you, you will know what I'm trying to send. So you can tensorize the channel to improve. So channel capacity tells you that what is the number of bits that you can, NATs that you can send per use of the channel while letting it be reliable. This is the sort of the definition of channel capacity. And Shannon proved that this thing is really equal to this object. It's equal to the mutual information over all inputs and corresponding outputs. It's equal to the maximum mutual information, which has a nice formula. It is entropy of the output minus the entropy of the output given x. So in our case, this simply becomes the formula over there. So the channel capacity, K was something. The channel capacity is the supremum over all x of that object over there, the mutual information between x plus z and x. So by what I proved that if you contract the set K, the channel capacity of the Gaussian noise would decrease if you communicate over that particular alphabet, which in Alice Bob language is written in this manner. So so I will just say one more thing, and then I will. So the next slide is the thank you slide. But I will say one more thing. That I will advertise my problem that I proposed in the open problem session again. So what we proved, the entropic Kneser-Poulsen or this, it is dimension free. Doesn't care about dimension. The actual Kneser-Poulsen conjecture is very dimension free. You add a ball. So this is why the Kneser-Poulsen conjecture is unknown, and I showed you a relatively simple proof of the entropic version.
But you have many formulas where density was whatever, so suppose the density is just the density of the convex body or ball or something. Ball.
Yes. For the Gaussian, I'm saying that the entropic Kneser-Poulsen is a dimension-free
The
quantity.
calculations were for general.
Yes. So I showed that at this step, right, I really needed the Gaussian.
Okay.
I really needed the Gaussian, but I think it should work for radially symmetric log concave. And if what we proved, what I am calling the entropic Kneser-Poulsen for all Renyi entropies. If you prove this for the uniform noise on the ball, you prove Kneser-Poulsen conjecture. Because Renyi entropy of order 0 is just the log volume of the support. So it's but this is dimension free. I would have the channel capacity doesn't see of the additive Gaussian noise, doesn't see which dimension you're sitting in. So it is a dimension free thing. On the other hand, so this was a question that I asked yesterday in the open problem session. So this would be I will just can I turn this off?
Yes, there's an AV mute, I think they said. There's a white remote somewhere here. There's a white remote, thicker white remote.
I think I just, like in this moment, my location skills are a little poor, so oh, thank you. So this is a problem that I proposed in the open problem session last time. And as I said, this is a refinement of what we proved, the theorem I showed to you. And also this contains Costa's EPI. If you apply to scalings, if Tx is lambda x for lambda, so if Tx is equal to lambda x, and lambda is between 0 and 1, a yes would be equal to Costa's EPI. So this is like a common generalization of Costa's API and the entropic Kneser-Poulsen that I just showed you. And of course, this is, at least to me, this is not, it's not a dimension-free inequality that I'm asking. This is, so I don't know how to prove this. So of course, you can try to follow through our arguments and prove it for continuous contractions. By of course, I don't know how to, but it is probably possible. But from continuous contractions, I don't know how you would go to. This is, I think it's a good problem. With this, I will thank you for listening.